Hello everyone, welcome back to the video tutorial series of the operating system. I am your instructor Varshada. Let's start our lecture series. So at the end of this video, you will be able to learn about the memory compaction, memory abstractions, then we will see the multiprogramming without memory abstractions, then we will see the static relocation, base and limit register, and then we will see the dynamic relocation and how we are able to free the memory. So managing free memory. So this topic we will see in this lecture. Now let's start with the multiprogramming with the dynamic partitions. Okay, so in last lecture we have studied about these dynamic partitions. So just let's recall it. Okay, here in this figure you can see when you are going to do the dynamic partitions, what will happen? One portion of the one portion of the memory that will be reserved for the operating system. So operating system is lies everywhere in each partitions. Okay, so it will be the first partition of the operating system, and whenever any new process will come, so at that time every new process will be assigned according to that process size. So here you can see in first the process A is there, after that process B will be assigned, after that process C will be assigned. Now what will happen? The process A has completed its task and now A will release its memory. Okay, and another process B comes, so that will be assigned to the partitions of the A because it was the larger partition than the space that is available. Okay, so here B will be assigned to at the place of the process A where it is stored. After that, suppose B process has completed its task, so it will be free. It will free its spaces. Okay, so like this way the memory allocations will be there every time. Okay, and again suppose the process A comes again, so process A will be reallocated again. So these things will happen again and again in the memory partitions. So what will be there? We have to compact that memory. When we assign much more memory, we know the external fragmentation is there. So if the external fragmentation is there, we have to find out some solutions for that. Okay, so this is what the multi-programming with the dynamic partitions. Okay, so what we have to do? We have to do the memory compaction. In last slide, we have seen that scattered memory is there. So we have to combine this scattered memory to provide useful space and to provide the continuous space. Okay, so we have to combine this scattered memory. So here when the swapping creates multiple holes in the memory, it is possible to combine them all in one big hole by moving all the process downward as far as possible, and this technique is known as the memory compaction. Okay, what we have to do? We have to combine all the scattered free memory. Okay, one side, and the process that still now working in the memory to the one side. Okay, so that means what we will able to find out the area of the memory that is currently using by the processes and the area of the free memory, so that we can allocate newly arrived process to that particular area. But what is the disadvantage of this technique? It requires a lots of CPU time. Why? Because every time CPU have to find out where the memory is free. Okay, so every time CPU has to find out where the memory is free, it has to link all this free memory, it has to link all the active processes. So the workload of the CPU will be more in this memory compaction. And here in this figure you can see this processes are the process A is working and process B is working, means they are in the active state. And here the process between the process A and process B, there is a free space. So what we will do? We will move this process B towards to process A. So there is a continuous allocated space and there is a continuous free space. So that is known as the memory compaction. Got it? Now, next is what is memory abstractions. How we can define this memory abstraction? Okay, so the hardware and the operating system, memory manager makes you see that memory as a single continuous entity. Whether the processes are scattered in the memory allocation, then also you are able to see that it is a continuous allocation. That means you don't have the idea about where that your process is stored, you will continuously get access of it, but you will not get where this process is stored, whether it is a continuous, whether it is a non-continuous, or whether it is stored at a different locations also, at a different hardware device also. You don't know anything about this. So that is known as the abstractions. Okay, and how this memory abstractions will how this hardware do everything, that is because of this abstraction. So that is known as the memory abstraction. Now, multiprogramming without memory abstraction. If memory abstraction is not there, then what will happen? Let's see. Okay, so for example, here there is a one program, that is a program 1. Okay, and here you can see the address of this program 1 from 0 to 28-bit. There are numbers of instruction is that. Just I have given this 2 or 3 instructions, but lots of instruction is there in this program. Same way there is another program, that is program 2, and again there are lots of instruction there in this program 2. But when this program will be loaded in the memory, what will happen? For example, okay, so this is the memory locations. So here you can see this is the program 1 and 2, that is loaded in the memory. Okay, so here this is a program 1 and here this is a program 2. Okay, so now what will happen? For program 1, everything is fine. Why? Because it will load it from the starting address 0, so we don't have to relocate that particular program. A relocation will not be required for program 1. But program 2 is loaded in this particular area of the memory. Here the starting point address is what? 16,380, that you can see in these slides. Okay, so this is the starting point of the program 2. But now what will happen? Here you can see the jump instruction is that is jump 28. But here jump 28 will not work. Why it will not work? Because at 28 number there is another instruction that is stored, that is add. So this program will not work properly. Why? Because there is no proper addressing is there. Okay, so this is what memory addressing, multiprogramming without memory abstractions. Okay, so what we have to do? We have to change these instructions to a particular address. Okay, so that when the program will execute, it will jump to that particular location. Got it? Okay, so using the absolute address is wrong here. Here we are using the same absolute address in the program 2. So that is the wrong. Okay, so we can use the static relocation at the program load time. So we have to change this particular address so that program can run properly. So this is what the multiprogramming without memory abstraction. Now let's see the static relocation. Okay, so here you can see we have changed the address number here for the jump 28 rather than the jump 1644112. Okay, so when the program was loaded at the address, that is the 16,384 address, at the constant 16384 was added to every program address during this load process. Okay, because program has started from the loading 16,384 address. So what we have to do? We have to add this constant to each and every instructions of the program 2. Okay, then and only then we will get the proper address for each and every instruction and program will run completely. Okay, so it's required the extra informations from the program. Okay, and it is slow. So that is a 2 disadvantage of it. It is slow because every time we have to change the address of each and every instructions. So it is little bit slow than the actual execution of the program, and it required the extra informations from the program. That means the extra information like where the instructions will be jumped or from where the instructions will be stored, everything the information that will be required by the program and this. So this is known as the static relocation. Okay. Now let's see next topic, that is a base and limit register. Now what is the meaning of this base and limit register? In last slide and last to last slide also we have seen a program in which there is an address and there is also limit. Okay, so let's see what is this base and what is this limit. Okay, an address space is a set of the addresses that a process can use to address the memory. So what is address space? An address space is a set of the addresses that a process can use to address the memory. An address space is a it is a range of the valid addresses in a memory that are available for the program or process. Okay, so it is a range of the memory. So two register is that, which are two register? Base and limit register. Okay, so base and limit register is that. Now what is the base register and what is the limit register? Base register, that means it starts the address of the program in a physical memory. Okay, and limit, that means what? The length of the program. From where the program physical memory starts, that is the base, and to which address this program will end, that is the limit register, that means the limit of that program. Okay, so for every memory address, base is added to the address and result will be compared to the limit. Okay, so for every memory access, in last slide also we have seen that 16,384 constant will be added to each and every instructions, because it was the starting point of that particular program. So that will be added to each and every instruction, and also it will compare with the limit register, that is the last point of that particular address. Okay, so it will compare to that. If it is less than that limit register, then it will be added to that particular instructions. Okay. Only operating system can modify base and limit register. User cannot modify the base and limit register manually. That will be done by operating system only. Okay, so here you can see this program. Here you can see this is the base register. That means the base address for the program 1 and program 2. And this is the limit address for the program 1 and program 2. So for our program 1, that is a base address from 0 and limit, that is a 16,380. And for program 2, the base is 16,384 and here its limit is 32,764. Got it? So this is the base register and this is the limit register. Now next is a dynamic relocation. So what is dynamic relocations? Okay, so first of all, when we are doing the dynamic relocation, so here you can see the hardware adds the relocation register to the virtual address to get the physical address. Okay, so hardware, what hardware will do? Hardware adds the relocation register, that means the base register, base address, to the virtual address to get the physical address. So virtual address, that will be generated by the CPU, and physical address, that will also be generated by the CPU, but the physical address, that means what? When the program it gets the actual execution, at that time the address that is defined, that is known as the physical address. Okay, so logical address will be added to the base register and it will define what the physical address. Now what hardware will do? Hardware will compare address with the limit register. So it will compare the address with the limit register. If it is a less than limit register, then and only then this is possible. Okay, so hardware compares the address with the limit register and address must be or less than or equal to the limit register. If test fails, okay, if test fails, then it will generate the error. Okay, and if it is less than this limit register, then the relocations will be done. So as we have seen in last slide, that program 2 is relocated to the different addresses. Why? Because already program 1 is there at the same addresses of the program 1. So program 2 cannot be relocated at the same place because program 1 is there in the execution. So program 2 will be relocated to the another space, and every time this base address will be added to each and every instructions. Got it? So that is known as the dynamic relocation. Okay. Now managing the memory. So how we are able to manage the free memory? So again there are two ways. One is a bitmap and another is a linked list. Okay, so let's see it. With bitmap, memory is divided into a location unit. Okay, so memory is divided into allocation unit, and corresponding to each allocation unit there is one bitmap for each and every unit. So bit is 0, that means the unit is free, and bit is 1, that means unit is occupied. But what is the main problem with this? The main problem is that when it has been decided to bring a k unit process, the memory manager must search the bitmap to find out or run k consecutive 0 bits in the memory. So what is the problem? If you want to find, suppose there are 50 bits of bitmap is there, and suppose you find out the 40 bit. So what you have to do? You have to starting to search from the end to 40 bits. Okay, so that will be the problem with the bitmap. That means you have to consecutive search in each and every bit. Searching a bitmap for run of a given length is a slow operation. So this is the disadvantage of the bitmap. And next is a linked list. Now what is the linked list? Another way to keep the track of the memory is to maintain the linked list. Now all of you are aware about the linked list because you have studied it in the data structure. Okay, so I think you have idea about the linked list. Okay, so linked list of allocated and free memory segment. So when segment either contain a process or it is an empty hole between two processes. Okay, so it will contain the entry for P and H. H that means holes and P that means a process. Okay, so which it starts, address at which starts and length and a pointer to the next entry. That we will see in the figure, so you will have the better idea. The segment list is kept sorted by the address. Okay, and sorting this way has an advantage. What is the advantage? So when a process terminates or it is swapped out, updating the list is straightforward. Okay, so it will be in the sorted form. So whenever you want to update the list, whether the process arrives or whether there is a hole, so it will be very easy for you to keep track of each and everything. A terminating process normally has two neighbors. Okay, two neighbors except when it is at the very top or the bottom of the memory. Now here you have the better idea about this bitmap and the linked list. So here you can see this is the same string that is used for the bitmap and that is used for the linked list. So here you can see how the bitmap is defined. So here you can see one is allocated for the 1 unit, again one is allocated for the 1 unit, again one is allocated for the 1 unit. So here this 1, 2, 3, 4 and 5 and 6 consecutive one is there. Okay, so here, sorry, 5 consecutive one is there, that will be allocated, and here free space that is defined by this dashed line. Okay, so like this way you have the bitmap for each and every unit. Okay, so this is the way of defining the bitmap, but it is a bit complicated. So there is another solution, that is a linked list. So here you can see there is a process. Okay, so that is of the 5 bits. So here you can see there is a process. Okay, so that's why it is a P. It is starting from the 0, so that it is starting from the 0, so that why in that box it is written 0, and length of that is a 5 bit. So here you can see P05. That is the format. Got it? After that there is a whole of the 3 bit. Here you can see 30 is that. Okay, so it is a whole of the 3 bit. So here whole starting from the 5 ends up to the length of that whole is a 3. Got it? So whole, 5 and 3. So this is the syntax for the whole. After that another node is there in which again there is a process. Okay, process P starts at 8, length is 6. Okay, and next is again a process that starts at 14, length is 4. After that there is a whole, that is a start at 18. Here you can see, and length is 2. So like this way linked list is defined for this memory management and bitmap is defined for this memory management. Okay, so in this video we have learned the memory compactions, and then we have seen what is the memory abstractions, and then we have seen the multiprogramming without abstractions. So if we will do the multiprogramming without abstractions, what will happen? Program will not get the exit address when it is there in the execution. So instruction should have the proper addressing so that the program can continue execution properly. Then we have seen the static relocation. So we have seen the how to change this instruction's address, and then we have seen what is the base and what is the limit register, and then we have seen the dynamic relocation, and after that managing the free memory using the bitmap and linked list. So this is all about this lecture, and many interesting topics we will cover in the next lecture. Thank you for watching. Thank you.